Assalamualaikum warahmatullahi wabarakatuh. We are from Group 10 of PBL assignment for network analysis. In this video, we will be presenting our group assignment that consists of 4 main components, which are objective, calculation, simulation, and discussion. We will start the presentation with objective.
Assalamualaikum warahmatullahi wabarakatuh. My name is Afika Himni binti Yusof and I am from Group 10. So, I represent my group to explain about the objective of the assignment that had been given from the lecturer. This is the objective of our assignment. There are 5 of our objectives. First of all, as we know, the main topic of this assignment is known as AC power analysis, power factor correction. So, my first objective is increase knowledge in analyzing AC power. By using the information that had been given in the question, we need to use the value correctly to get the value for the calculation. And next, the objective is to train us to identify the correct formula and technique to use during the calculation. As we know, there are a lot of formula in this topic, but we need to figure out the correct formula based on the information that we have. Next objective is to improve the skill using simulation that related to the circuit and to investigate the possible cause for the loss. At the end of the assignment, we will need to compare the calculation and the simulation results. Both results will surely have a few differences, but from there, we will figure out what are the possible cause of the differences. Last but not least, the objective of this assignment is to improve the understanding of the student for this topic. Improve the understanding for this topic for each of us when every group members are required to calculate the answer for the questions. So each of the group members will eventually improve their understanding of this topic and help each other to get the correct answer. By the way, we will also need to compare our result from the other groups, and we also need to compare our result from each of our group members so that we will have the correct answer and we can proceed to the other task.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nafati Ahmadullah Shahid and now I'm going to present task 1 calculation. Okay, from the question, we know that the other parameters such as load 1, load 2, load 3, the value of transmission line 1 to 2, line 2 to 3 and line 3 to 4. So these are all the value that I have given in the question. So after we summarize all the value given, so this is our group finalized design for the task given for our group. For the first question, which is question A, we have to find the impedance for each load and the equivalent impedance. So first of all, we're going to find load 3 as only load 3 are given voltage at it. So we're going to start with load 3. We're going to use formula S equal to P plus JQ as P and Q has been given. So these are the final answer for S3. So by using complex power, then we're going to use formula S equal to V3 squared divided by Z3 conjugate, and we're going to get the Z3 for load 3 impedance. As we get the value of Z, then we can find the I3 by using the Ohm's law, which is V3 divided by Z3. So this is the value of I3. Next, we're gonna find the Z3T, which is the sum of the transmission line value and the load 3 in order for us to calculate the VT by using Ohm's law, which is IR. So as we get the voltage at this node, so V3T is equal to V2 V at load 2 as they are placed in parallel. So we're gonna move to load 2. Load 2, we're gonna use formula P equal to S cos theta, as we were given the value of V, the value of P, and the value of PF, which is cos theta. So we're gonna find the value of S. We substitute the value that we had been given. Then we're gonna find the angle for this complex number. So this is the complex number for load 2. So as we had obtained the complex number, then we're gonna use the same formula as load 1 in order to find the Z2, Z load at load 2. We're gonna have to parallel these two in order for us to find the I that flow in this line. So as we had parallel it, and we're gonna use Ohm's law in order at the value of I. Then we sum it out with the transmission line over here, and then we use the formula Ohm's law, and we get V2 at this node. So V2 at this node is equal to the V1 over here. Then we're gonna move to load 1. We're gonna use the same formula as load 2, as we had been given the same information on load 1 and load 2. So the formula we have been used is P equal to S cos theta, and this is the final answer. Then we find the angle. So we got the complex number. We use the formula S equal to V divided by Z, and then we got Z1. So this is the final answer for question A. The impedance for each load Z1, Z2, and Z3, and the given impedance is the total of Z1, Z2, Z3, and we sum it out with the transmission line given. So we move to question B, which is the main supply. So we had calculate the total of Z here after we parallel and sum it up. Then we got this final Z parallel. Then by using the formula of current divider rule, we're gonna find Vs over here. So we have already known V over here. Then we're gonna substitute the value that we have, and we got the answer Vs. Okay, we're gonna continue with question C. We have to find the current flow in each load and the total current supplied by the source. So we're gonna use formula Ohm's law, which is I1 equal to V1 equal to Z1 to all the current that we're going to find, including the I source, because we have got the voltage and the impedance at each load. So these are the value that we obtained for I1, I2, and I3. And for I source, we use the V source divided by Z total. So this is the current supplied by the source. So for D, we have to find the real and reactive power loss at the transmission line. So the formula that we're going to use is S equal to I squared Z. For Z, we're just going to use the transmission line value. So for S12, this is the value that we got. So S equal to P plus JQ. So from this we get to know the value of P and the value of Q. So we use the same formula for line 2, 3 and line 3, 4. So the question E, we are asked to use to find the total apparent power, real power and reactive power of the system, and we have to determine whether the system is leading or lagging. So we are going to use formula S equal to VI conjugate. We're going to find total apparent power, which is ST, and we're going to find VS times IS conjugate. This is the value, and this is the I that had been conjugate. So we got this value P plus JQ. So we had automatically we got the P, which is the real power, total real power, and total reactive power. As for apparent power, we have to convert it into polar form and take the magnitude as its apparent power. So in order to know whether the system is leading or lagging, we look at the angle. As the angle is positive, so the system is lagging. So we're gonna find our power factor So for vector cos theta equal to P divided by S, so this is the value, and then we got PF equal to 0.905. Okay, for the last questions, we are being asked to draw a complete quadrangle. So this is the complete quadrangle. This is the ST, apparent power total, Q reactive power total, and P real power total. This is the PF that we got earlier, and this is the angle for the total power triangle ratio is lagging. Okay, that's all from me. Thank you.
Assalamualaikum. My name is Safika Yumi, and today I will explain about the calculation for the task 2. The question given for the task 2 is based on a network that you design in task 1. Design the power factor correction system that helps to improve the system power factor to 0.98 lagging. So first of all, as we all know, power factor is equal to cos theta. So we had been given from the question that power factor is equal to 0.98. So from this power factor, we can find our new theta. So cos theta is equal to 0.98. So our new theta is 11.478. This new theta we will use in this power triangle. So this is the value of theta new. This is the value of S, Q, and P. Next, we will calculate the value of Q new. The formula that we use to calculate the Q new is Q new equal to P tan theta. But the value of theta we use is theta new, not the theta O. Theta new that we have been calculated just now. Q new equal to P tan theta, so P is 356.04454. This is the value that we get from task 1, from calculation from task 1, and tan, and this is the value of theta. So the answer is 72.297 kVAR. Next, we will calculate the value of S new. The formula that we use for S new is S new equal to P plus JQ. P is the same like Q new. We use the same value for P for in Q new and S new. So this is the value of P. Plus JQ. We use the value of Q new that we calculate just now, which is 72.297 kilo. So this is the final answer for S new. So the next steps is to draw the power triangle. We can obtain the value from the previous calculations. So in this power triangle, we have QO, Q new, S new, and SO. QO and SO we obtain from the task 1 calculation, which is that had been explained by my friend. The value of QO is 167.64 kVAR and SO is 393.547 kilo. So this is the S new that we had calculated just now, and this is the Q new. From QO and Q new, we can also calculate the QC. So the formula for QC is QC equal to QO minus Q new. So this is the value of QC that we obtain. We need to find the value of QC so that we can enter the value in this formula. QC equal to modulus V squared R to pi FC. 2 pi FC is equal of these calculations. We need to find the value of C in our task. Value of QC and the value of V squared 2 pi F 50 Hz that had been given from the questions, and C is the value that we want to know. After we substitute all the values, at the end of this task, we managed to calculate the value of C is equal to 2.575 milli of C that we obtained from our task. Thank you.
Hello, my name is Muhammad Aiman Ramlan, and I'm going to explain briefly about the simulation process of AC power analysis and power factor correction. For this simulation process, we are going to use the single frequency AC analysis. This is because the single frequency AC analysis could measure the accurate value by using the complex number format, which we can set either we can use the magnitude and phase value or the real and imaginary value. Okay. But to use the single frequency AC analysis, firstly we must set the AC analysis magnitude and AC analysis phase at the voltage supply. For example, my group has set the AC analysis magnitude at 343.34 volt, while the AC analysis phase at 30.953 degree. Now I'm going to explain a little bit about the circuit diagram. The little red number over here is actually represent the value of the voltage that across the voltage next to it, which is known as voltage net and the number. So for example, the voltage net across this for this connection is voltage net 9, and I also tick the show net name so that we can easily refer the voltage net for the single frequency AC analysis. So that means the voltage net 9 is actually the voltage of the load 3. Now I'm going to explain about the single frequency AC analysis. The single frequency AC analysis could be used to measure the circuit voltage across the element and current of each connection, and we can simulate each of the value by selecting all the variables in here, and also the single frequency AC analysis could be used to measure the power dissipated in the circuit. So to use the single frequency AC analysis, we must first set the frequency. We may ensure that the frequency must be tally with our voltage supply here. For example, my group has set the voltage supply at 50 Hz, so we use 50 Hz. And for the output here, the frequency column is an option whether we want to display the value of the frequency in the analysis or not. And the complex number format is actually the value of the analysis, whether we want it on the value and phase value or real and imaginary value. Okay, so I'm going to set the value to the magnitude and phase. Okay, I'm going to show some examples on how to measure the voltage. Okay, so let's say we want to measure the voltage of transmission line 3 to 4. The voltage at transmission line 3 to 4 voltage is between the voltage net 6 and voltage net 9. So there is no variable for that, so we must add an expression. So we could use the operation of minus. Voltage net 6 will be minus with voltage net 9. See, we can so there is the variable for that. So this is the voltage value across the transmission line 3 to 4. For the voltage across the load 3 is the voltage is equals to voltage net 9. So we select the variables voltage net9 and then click simulate. So this is the analysis of voltage, and voltage net 6 minus voltage net 9 is equals to voltage transmission line 3 to 4, while voltage net 9 is equals to voltage across the load 3. Now we are using the single frequency S analysis to simulate the value of current flowing through an element. So the frequency is still the same, and the complex number format is still in the register and phase. So we're going to remove all the variables, and we're going to select the variables for the current. Let's say we're going to measure the current flowing from for current total, or the current flowing through the transmission line to 2. The current flowing at transmission line 1 to 2 is current flowing through the resistor 1 and inductor 1. So if you look at through the variables, the current could be selected with variables of IR1, or we could choose the IL1. Both of these variables are having the same value because the current flowing through the transmission through the resistor 1 and inductor 1 is actually the same. It's actually the transmission line current. So we click simulate. Okay, so this is the current flowing through the transmission line 1 to 2. We could also measure the current flowing at transmission line 1 to 2 by using the current Kirchhoff law. For example, the current that flows at transmission line 1 2 is equals to current flowing at transmission line 2 to 3 and transmission and load 1. So I'm going to select the variables and add an expression because it's involving an operation. So voltage current flowing at transmission line 2 to 3 is equals to IR2 plus with current flowing at load 1. So current flowing at load 1 is equals to IR4. Okay, and then we click simulate. So as you can see, the Kirchhoff law will simulate the exact same value as the current flowing at the transmission line 1 to 2. That's it for the simulation of the current. Next, I'm going to explain on how to measure the true power and the relative power value by using the formula of apparent power, which is S is equals to V times conjugate of I. So from the apparent power, we could we could get the value of for both true power and the reactive power by the real and imaginary value, which is S is equals to P plus JQ. So P, which is the true value, will represent the value as the true power, while the imaginary number will represent as the reactive power value. So now I will simulate an example for, let's say, how to measure the power at load 3. So we're going to set the complex number format at real and imaginary value, so that we can obtain both true power and complex power value. So at load 3, we're going to use the formula F is equals to V times conjugate of I. So voltage that across the load 3 is equals to voltage net 9. So we're going to select voltage net 9 and times with the conjugate of I. Because I doesn't have the function of conjugate of the conjugate, so I'm going to use the complex function, which is the real and negative imaginary value of the current. So the real and imaginary will be selected by using the current flowing at load 3. So current flowing at load 3 is equals to IR6, and the imaginary will also be using the IR6. So simulate. Okay, simulate. So this is the apparent power that are dissipated at load 3. So the real value of the apparent power is the true power of load 3, while the imaginary value is representing the reactive power at load 3. Okay, but now I'm going to show you how to measure to simulate the true power and the power the reactive power at transmission line 3 to 4. We can use the same method as the apparent power at load 3. S equals to IV. So voltage at transmission line 3 to 4 is equals to voltage at net 6 minus voltage at net 9. So voltage net 6 will be minus with voltage net 9 will be times with real value and negative imaginary value of current flowing at transmission line 3 to 4. So current flowing at line 3 to 4 is IR3. So imaginary also will be used the IR3, and then we could simulate. Okay, so this is the apparent power that dissipated at transmission line 3 to 4, and the real value is the true power, and the imaginary value is the reactive power. Okay, so next I'm going to explain a little bit about the power factor correction step. So during power factor correction, for example, the system had been improved to the 0.98 lagging power factor. So after the calculation has been made, the shunt capacitor had been connected parallel to the voltage supply. So during the power factor correction, the system are experience the new apparent power and the complex number, while the true power are still remain the same. So we're going to prove it by also using the complex number format of real and imaginary to get the both true power and complex number format, like true power and the reactive power value. So I'm going to remove the variables, and we're going to get the new apparent power and the new reactive power by using the S equals to V times I formula. So the apparent power that are being simulated is at the supply. So we're going to use the voltage as the V1 times the conjugate of I, if imaginary. Okay. For the current flowing at the supply is coming from the Kirchhoff current law by adding the current flowing at transmission line 1, 2 and the current flowing at shunt capacitor. So IR1 will be plus with current IC2, the imaginary also having the same value, IC2. Okay, and then simulate. So this is the how we check the power factor correction value of the new apparent power and the reactive power after power factor correction. So that's it for the simulation explanation. Thank you.
Moving on, we will proceed to task 4, which is analysis and discussion. First of all, my name is Nurul Najah Najwa binti Rahim, and I am from Group 10 of PBL Assignment Network Analysis. In this task, we will be discussing about the comparison between simulation and calculation results, and also we will be discussing about the effect of power factor correction. As you can see here, we have a table of comparison between result of apparent power from calculation and simulation. As you can observe from the table, the value of the calculation and simulation is not too much difference. They only differ by average of plus minus 1. The difference is caused by some reason, which are losses occur at the transmission line in the circuit, and the calculation values are fixed because they use specific formula. Last but not least, we will discuss about the effect of power factor correction. After both calculation and simulation done for power factor correction, the power factor increased to a value closer to 1. The ideal device has unity power factor, which is good. The circuit is close to be purely resistive load and also have higher linearity. As the conclusion, at the end of this assignment, students get to understand the AC circuit analysis and also the importance of power factor correction.